Okay, so we've come to the third part of our lesson in algorithm, which is complexity of algorithms. Okay, so we will answer the questions: what does complexity of an algorithm mean, and why it's important to know or measure algorithm complexity, and how do you evaluate the complexity of algorithms? Okay, so what is algorithm complexity? Algorithm complexity is a part of the analysis of algorithms that evaluate its efficiency. Okay, it is also known as computational complexity. Now, there are two kinds of complexity. Okay, so you have time complexity and space complexity. Time complexity, or otherwise known as, or also known as running time, it answers the question: how long will it take the algorithm to solve the problem? No, it does not mean in seconds. So it means based on the iterations. Okay. For space complexity, it answers the question: how big is the memory requirement for the algorithm? Okay, so for this discussion, we focused on time complexity, or the running time. So running time can be expressed in terms of the number of operations used by the algorithm with respect to the input size. So basically, um, it describes how the algorithm grows with respect to the input. Okay, so it can be measured in three ways. You have the best case, or the big omega, the average case, which is the big theta, and the worst case, which is the big O. So naturally, we'll focus on the worst case, because if your algorithm performs well based on the worst case, then how much better would it be in the best and average cases, right? Okay. Okay, so we call these three notations, or we define these three notations mathematically as the growth of functions. So mathematically, if you have two functions f and g, which is a mapping from z to r or from r to r, and if there are constants c1, c2, and c3, and another constant k, such that one of the conditions in the second row of the table is satisfied, then you can say that f is said to be of order corresponding to the growth of the function indicated in the first row. Okay, so for example, in the best case, in big theta, the definition of that is f of n should be, the absolute value of f of n is greater than or equals c times g of n. So it provides the lower bound. That's why it's called the best case. Meaning, okay, so yeah, that's it. And then the big theta naman is defined by this. So f of n is bounded below and above by g of n, subject to some scaling, or the values of c1 and c2. That's why it's called the average case. For O of n naman, you have f of n being bounded above by g of n, subject to a certain constant c. Okay, so that's why it's called the worst case. So the algorithm can perform as long as its worst case is here. It's defined by g. It cannot go beyond that. For the best case, the algorithm can perform, but you're able to identify its best case. That's the lower bound. Okay. So when you say f is of order theta, if it is of order omega and O of n, since theta is best case. So when you consider growth of functions, you can ignore the constants. You only take note of the terms that dominate others. So in the concept of algorithms, we will present this, or we will discuss this further by trading, or by identifying the number of operations in an algorithm. So for example, look at this. A constant time of, or O of 1, is what we call an algorithm that is independent of the input size. So no matter what the input is, it still performs uniformly at a constant time. So for example, this one. If you assign x, if the algorithm the only task of the algorithm is to assign x the value of 3 plus 4 minus 3 times 4, if you look at it, the values are constant. So it is not dependent of the input, right? So, and if you look at it, the number of additions, we have two additions. You have one multiplication, which is a total of 3 operations. So the order for that is 2 times O of 1. That refers to the addition. And then for multiplication, that is O of 1. And then for, so why O of 1? Because one operation is O of 1. Okay, so in total you have 2 plus 1, so that's 3 O of 1. And since we ignore the constants, so generally this is O of 1, that is constant time. Okay, now some analysis also considers the assignment of values as an operation. So in this case, the value of this, of 3 plus 4 minus 3 times 4, is assigned to x. So we can add one more operation, which is assignment of value. So we have 4. Okay, so we have 2 times O of 1 for the addition, O of 1 for the multiplication, and another O of 1 for the value assignment. So which is equal to 4 O of 1, which is just O of 1. So even if we consider that, our complexity is still of constant time, or O of 1. Okay, so you study this first, you pause the video and study this, and check your answers in the next slide. Okay, so for example, x equals 3, you only have one operation, which is assignment, so O of 1. So for this case, 3 plus 2x, you have multiplication, which is 1, addition, which is 1, so that's 2, assignment is 3, so that's still O of 1. 3 times O of 1 is O of 1. Okay, now this case, you have multiplication, which is 1, subtraction, which is 1, assignment, which is 1, so 3. So 3 times O of 1 is still O of 1. And then, so when you print, well, if you assume the value, so this is 1, 2. Subtraction is 1, addition is 1, and then you print it, that's another 1, so that's 3. But basically, if you just focus on the print, so that's just one operation. So that's O of 1. If you consider the computation here, so that's 1, 2, and then 3. So that's 3 times O of 1, which is just O of 1. Okay. So these are all O of 1. So you have a total of 4 O of 1s, which is, again, we can ignore the multiplier, so it's just O of 1. So this block of code as a whole is O of 1, still of constant time, meaning not dependent on the value of the input or the size of the input. Okay, so study this algorithm and try to answer to determine their complexity. So there's a clue, this is of complexity O of n, meaning it runs in linear time. So the size of the input is proportionally affecting the growth of the algorithm. So linear yung growth nila. Okay. Okay, so let's discuss this one by one. For the first example, if you look at this, the only thing that the algorithm does is to print I every iteration. But the iteration runs from 1 to n. Okay, so the print I is O of 1. But since you're executing this whole block n times, then that's n times O of 1. But n is a variable, so you cannot ignore it. It's not a constant. So basically, this is O of n. Okay? Similarly, for number 2, the first line is value assignment, so that's O of 1. Then the next block is similar to example 1, okay? Which is O of n, right? So this is O of 1 plus O of n. So O of n is unknown, it's a variable, so it's bigger than O of 1. So basically, when you add them together, O of 1 becomes negligible. So in result, we have O of n. So if you notice, if the lines are adjacent to each other, you add them. But if a line is implemented multiple times, then you multiply its complexity by the number of times it is being implemented. So O of 1 is implemented n times, so O of n. But the first line, which is just adjacent to the block of code, is O of 1, and you just add it to O of n. But again, it resulted to O of n. Okay. Now this example shows quadratic time. So the number of operations grows in proportion to the square of the input size. Okay, so you study this first, then pause the video, answer it before proceeding to the next slide. Okay, so let's see. Now look at this. Print I times j is O of 1, right? But then this line is implemented n times. So that's O of n. But this whole block that's being implemented or run n times is again run for another n times the whole block. Okay, so that's another n times. So this is O of 1 implemented n times, that's n times O of 1, so that's O of n. Now this O of n is implemented n times, so that is n times O of n, or O of n squared. That's why it's quadratic time. Okay, so okay, study this and then pause and proceed. Okay, so look at this. This one adjacent, that's just O of 1. Print x is O of 1. Print x times I is O of 1. Okay, they're separate from each other. Now print x is implemented n times, so this whole block of code is O of n. Whereas print x sub I is O of 1 implemented n times, so that's O of n. But this whole block of code n times is also implemented for another n times, so that's O of n times n, so which is O of n squared. Now as a whole, so what do we have as a whole? We have this, which is O of 1, and then we have O of n, and then we have O of n squared. They're adjacent to each other, so we add them. So basically, you have O of 1 plus O of n plus O of n squared. That's O of n squared. So we always take the value of the dominant complexity. Okay. Now there are other orders of growth, such as the logarithmic growth or logarithmic complexity. This is not linear complexity. This is linear rhythmic complexity. That's n times log of n. You have polynomial complexity. You have exponential complexity and factorial complexity. So take note of this. What does this mean? This means that the fastest is O of 1. Next is O of log of n. Next is O of n, which is linear. Next is O of n log n. O of n squared, O of 2 raised to n, and the worst or the slowest is O of n factorial. Okay? So, if it is O of 1, it's the best, so it's the fastest. And then it gets worse as the complexity goes larger. So you take note of to study this, determine the complexity, and then we might discuss this in class or in the quiz. So we add this also.